Okay, thank you very much. Uh, it's a work that is related to the Shannon capacity of graphs, and I'll start with some necessary definitions. So first, I need to introduce a strong product of graphs. So consider G and H to be two arbitrary graphs that are finite, undirected, and simple, no loops, no multiple edges. And so we define the strong product G times H to be the graph whose vertex set is just the Cartesian product of the vertex sets of G and H. And as for the H set, two distinct vertices, GH and G prime H prime, in this strong product are adjacent if one of the following three conditions holds. In the first code, they are either equal in the first coordinate and adjacent in the second coordinate, or the opposite, they are adjacent in the first coordinate and equal in the second coordinate, or either they are adjacent in both coordinates. So the strong product is commutative and associative. And after talking about strong product, we can look at if G is a graph, we can view a strong power of a graph where G raised to the power of K simply means a strong product of G with itself K times. So this is the K-fold strong power of a graph G, where G is finite, undirected, and simple. So why I introduce these definitions? So far, any questions? Please let me know. Okay, so I introduced these definitions because I now want to move forward and talk about the Shannon capacity of a graph. So the Shannon capacity of a graph G is defined as the supremum of the case root, case order root of the independence number of G raised to the case power. So this is the k-fold strong power of G. You take the k-fold the strong power of G, look for the independence number of this graph, and then take a root of order k. And due to the supermultiplicativity of the independence number, using Feket's lemma, it can be shown that this supremum is actually also the limit where k tends to infinity of the same expression. The motivation for introducing the Shannon capacity of a graph in the seminal paper by Claude Shannon from 1956 was information theoretic, where he actually was interested to consider zero error information theory and modeled a communication channel by a confusability graph, meaning that you have a statistical characterization of a channel, and you create a confusability graph where two vertices are adjacent if they can be confused. Two input symbols are adjacent if they can be confused by the channel. And this is called the confusability graph, and the maximum rate at which reliable communication is possible with no error at all can be shown to be just this expression that is the Shannon capacity of the graph. Because you look at the independence number, you need symbols that cannot be confused. So you take k-fold sequences and you look at the confusability graph of these k-fold sequences, And then you can take the root of order k and let k be arbitrary by having this supremum. But it turns out that this Shannon capacity is very, very hard to compute in general. And even a cycle of length 7, its Shannon capacity is not known so far. So we are talking about something which has been introduced in 56, and even today, a cycle graph of length 7, its Shannon capacity has not been yet determined. So because of that, it's natural to ask about bounds, lower bounds, upper bounds, to get some computable bounds in order to compute the Shannon capacity of a graph. So there is a Lovász theta function, theta of g, that is formulated here as a semi-definite program and is shown in a paper by Laszlo Lovász from 1979 to be an upper bound on the Shannon capacity. Now, due to the progress in convex optimization, this function of a graph G is polynomial time computable, so it's practical to compute it, and it forms an upper bound on the Shannon capacity of graphs. How good this bound is? Well, sometimes it gives exact value by just comparing the upper and lower bounds, and it tends to be the Shannon capacity of the graph for Kneser graphs, for all Kneser graphs, as well as for self-complementary vertex-transitive graphs, which include, for example, a cycle of length 5. So the cycle of length 5, its Shannon capacity has been determined 21 years after Shannon introduced the Shannon capacity of graphs, and it is known to be the square root of 5. But in general, there is no guarantee that the Shannon capacity coincides with the Lovász theta function, and in fact, Hammers introduced another bound, and by some counterexamples show specific cases where the Shannon capacity and the Lovász theta function do not coincide. Okay, so this I already said, that the Shannon capacity is upper bounded by the Lovász theta function. So since the Shannon capacity and the Lovász theta function are not necessarily identical, but the Lovász theta function is an upper bound on the Shannon capacity, there is another variant of the theta function due to Schrijver, which is called the Schrijver's theta function, and we denote it by theta prime of g, in contrast to theta of g, that is the Lovász theta function. And it's again formulated as a semi-definite program where the only difference is an additional inequality constraint. So we say maximize of the trace of B times the all ones matrix and by M matrix, subject to the constraints that B is positive semi-definite and its trace is equal to 1. And whenever the adjacency matrix, the I and J, are adjacent vertices, Bij is restricted to B0. This was for the Lovász theta function. Now we also ask that all the terms, all the entries of this matrix need to be non-negative. And like the Lovász theta function, this can be computed in polynomial time because it's a semi-definite program. And the nice thing is that it turns out to be an upper bound on the independence number of a graph, which is sometimes strictly better than the Lovász theta function. You know that the independence number of a graph in general is NP hard to compute. So having a quantity that is polynomial time computable in the number of vertices is very useful. So the Schrijver's theta function is an upper bound on the independence number of the graph, and sometimes it is strictly better than the Lovász theta function. And I just want to remind you that the Lovász theta function is known to be an upper bound on the Shannon capacity of graphs. Okay, so it was posed in 1979 a question: can the Schrijver's theta function of a graph form an upper bound on the Shannon capacity? Maybe it could be a better bound than the Lovász theta function. And this thing was open since then. And the purpose of this talk is to show that the answer to this question is negative by presenting an explicit example where the Schrijver's theta function is strictly smaller than the Lovász theta function. And in spite of the fact that the Shannon capacity of that graph is not known exactly, to show that it cannot be an upper bound. I mean that the Schrijver's theta function for that graph cannot be an upper bound on the Shannon capacity of that graph. So this is the example, and it appears in a paper that was published 3 months ago. And for that reason, for that purpose, we considered G to be a Gilbert graph on 32 vertices. So that graph has a vertex set of all the all the binary 5 tuples, and the H set is just UV are adjacent if the Hamming distance between U and V is either 1 or 2. Okay? So EG is all the pairs UV where the Hamming distance between U and V is either 1 or 2. So they differ only in 1 or 2 coordinates among the 5. So this is a 15 regular vertex transitive, H transitive, and distance regular graph. This can be shown. And the complement of G is 16 regular, vertex transitive, but it is not H transitive, nor distance regular. And the fact that G is H transitive and G bar is not H transitive was a necessary condition for that for this an example to have a chance to form, to form an explicit expression for addressing this question. Because if G and G bar were both H transitive, then the Lovász theta function and the Schrijver theta function would have been identical. So in that case, alpha G is easy to compute. It's after all a graph on 32 vertices, and the independence number is 4, and this is an example of a maximal independent set. And solving the semi-definite program for the Schrijver's theta function, I just remind you, here it was, which depends on the adjacency matrix of the graph. We get that the Schrijver's theta function of the graph G is also 4, so it coincides with the independence number of G. So in that case, the Schrijver's theta function is a tight upper bound on the independence number. So on the other hand, since G is 15 regular and H transitive, and it can be shown that the minimum, the smallest eigenvalue, adjacency eigenvalue of the graph is -3, then the Lovász theta function is 5 and 1/3. This is the expression of the Lovász theta function when the graph is regular and H transitive. So in that case, we have that 4 is equal to the independence number, which is equal to the Schrijver's theta function of G, which is strictly smaller than the Lovász theta function of G, that is equal to 5 and 1/3. So the question is now, if also the capacity of the graph G is 4. If it is above 4, then this is an explicit example where the Schrijver's theta function does not form an upper bound on the Shannon capacity. And it can be verified, and in the paper we show such an independent set, that the independence number of G strong product with G, so this is the twofold strong power of G, is equal to 20. So it means that the capacity of the graph is at least the square root of 20. Whereas the Schrijver's theta function of the graph G is equal to 4. So it is strictly smaller than the square root of 20. And actually, there are many independent sets of size 20 of that graph, and this number was just found by the SageMath program for that specific graph. So this is just an example of a maximal independent set of G times G, strong product G with itself. So as I said, the Shannon capacity of G is at least the square root of 20, which is larger than 4, that is equal to the Schrijver's theta function. So as a summary, the Shannon capacity is notoriously difficult to compute. The Lovász theta function provides a polynomial time computable upper bound on the Shannon capacity, and for some remarkable cases, it is also tight. For example, the Kneser graphs and the self-complementary vertex transitive graphs. The Schrijver's variant is a polynomial time upper bound on the independence number, which is in general a better upper bound on the independence number of the graph. But as we have seen, it does not upper bound in general the Shannon capacity of the graph. So this resolves a 1978 query with a concrete example that is a Gilbert graph on 32 vertices, for which we see that the Shannon capacity of the graph is strictly larger than the Schrijver's theta function of this graph. And for all the details and the constructions and the way that it was verified step by step, you can consult with the paper that was published here. So here is the paper, and it is it can be downloaded. And by this, I conclude my talk.